Come on, video thing, and go where I want. There we go. You all hear me all right?
Yeah, I could hear you.
Yeah.
Got the fan and the air purifier going, so it's loud in here.
No, yeah, we can't hear that in the background, so it should be fine.
That's good. Thanks. Everyone have a good weekend?
That was pretty good, not too hot, so that's a good sign.
And that's the one advantage of there being so much smoke in the air that it blocks the sun. It's and you might have noticed that the forecast was like it's supposed to be 100 again, and it really wasn't. And that's just the ash is actually making a protective layer. It's actually kind of similar to sometimes what happens after volcanic eruptions, where so much volcanic stuff gets launched into the atmosphere that you get really bad winter. But,
I don't know what dinosaurs felt like.
Maybe, yeah. Actually, yeah, that's it's a good analogy. Of course, we didn't get the excitement of a space rock, but that's probably all the better that we didn't get that. But yeah, at least we aren't. Maybe some of you are in the Bay Area. I don't know, but did you see all those pictures of how San Francisco was orange?
Yeah, it's really bad up there.
Yeah, it's freaking crazy. If you're interested in checking the air quality, so I put a link to something. So if you're not familiar with Purple Air, it's a website that just uses a lot of like crowdsourced, like citizen science sourced air sensors that you can get. And we actually have one at CSUN in Live Oak Hall, and it's just like real-time tracking of the air. And if you look at it now, it's pretty depressing looking, but it's kind of it's a lot more locally specific than just like your weather app is going to be. So useful, especially if you are like me and have a chronic breathing condition.
Yeah, it looks pretty bad. I'm looking at it right now.
It's freaking crazy.
We're in like the 150s, kind of.
Which is the best it's been in a few days.
Let me see. Then up by the bay is like 180, 160.
They've also improved a lot. They were in the like 400s over the weekend. It's freaking crazy. Again, it kind of makes me wish we had room to actually talk about fires in this class. 400s in the Bay Area. There were some places, the highest number I saw was up in Oregon. It was like 700 and something, which is just absolutely ludicrous. But
yeah, I see a 770 in like the mountains.
I mean, it's going to be the worst near the active fires, but anyway, again, I wish we had time to talk about fires in this class for reals, but we don't. But anyway, it's 2, so I guess we should actually start the real class. I don't want to go over like last time. But anyway, today we're going to be moving on to talking about minerals. And but before I do that, I apologize in advance for any horrible sounds that are going to come out of my lungs during this lecture, because the air quality has been, as we were talking about, awful, and I have asthma. So I apologize if I have to cough really bad. I will mute myself. But sorry about that. Other logistical things. So minerals is our last topic before the first test. So our first test is 1 week from today, and it's going to cover everything from the first day of class up through our lecture this coming Wednesday. So there's another list of study guide bullet points for minerals up on Canvas now. The next quick quiz will be up right after class. And again, the way the tests are going to work is they're going to just be 30 multiple choice questions. And the class session is going to be, we're going to have just like 15, 20 minutes just to do a review. So I'll start Zoom right at 2 and you can ask me any last second questions. And then at like 2:25, we'll turn off Zoom and you can start the test at 2:30 and have until 3:15. So I'll talk a little more about the logistics next time and I'll send an email around with more details, but just keep that on your radar. So before I get into minerals, does anyone have any just general, logistical, whatever questions? All right, cool. Then let's talk about minerals.
Sir, I have one question. It would be a multiple choice, or we have to write the content in the description?
Sorry, it will be a what?
Multiple choice MCQ?
It will be a multiple choice test, yeah.
Okay.
Yeah. So all 4 of the during the semester tests are multiple choice, but then the final is going to be a written final. But yeah, and don't forget your lowest multiple choice test score drops at the end of the semester, no questions asked. But yeah, let's talk about minerals. So, you're like 4th grade earth science class or whatever, I guess 4th grade science class, because they didn't even divide it up by then, probably had this mixed unit of rocks and minerals, right? Does that ring a bell? Or like the Magic School Bus has the rocks and minerals episode or whatever. So what's the difference? Who knows what the difference is? And it's okay if you don't know, because for the most part, science classes don't start telling you the differences until high school or college. Okay. So that's all right. In that case, the very short answer is that rocks are made of minerals. Minerals are the building blocks of rocks. And we're not going to talk about rocks until after the first test. So minerals are on the first test, rocks start on the second test. But basically, well, I guess we kind of already talked about rocks with the light versus heavy, but we're not going to get into the details until after the first test. But the short answer is that rocks are made of minerals. Minerals are the building blocks of rocks. And because we talked about how the Earth is made of rock, then by extension, minerals are the chemical building blocks of the Earth. And so that's kind of the way I'm sticking the topics together for this first test. Like, it might seem like we talked about a variety of things, but ultimately it's all building blocks. Minerals are chemical building blocks. Plate tectonics is the physics building blocks. We talked about the chemical and physical structure of the Earth. And that stuff at the very beginning with the uniformitarianism, remember that? Was about how to read the structure and read the building blocks and put together the building blocks of a story of what happened. So in talking about minerals, again, we're going to talk some about just what they are, where they come from. So that's mostly what we're going to be doing today. And then on Wednesday, we're going to talk more about some specific minerals and the ones that are, especially the ones that are really important for making rocks. Because even though rocks are made of minerals, there are really only a pretty small number of minerals that are involved in the vast majority of rocks on Earth. So there's thousands of minerals that exist, but really only a handful of them are going to be particularly relevant to this class. Yeah, so building blocks, that's where we are. But given that these are chemical building blocks, we're going to have to talk about some very basic chemistry. So here's your periodic table of elements. And really, the ones involved in the minerals that we're going to be talking about a lot, again, there's really just a handful of elements involved. But you might know, just in case you're not familiar with reading this chart, the super, super, super quick and dirty, like, most relevant number to us is, so this atomic number speaks to how many electrons there are in that atom. And so we'll go ahead with that in a second. So atoms are, elements are the building blocks of minerals. Minerals are the building blocks of rocks. But there are building blocks to those atoms. And those are actually key in understanding how different kinds of atoms can join together to form different minerals, because it makes a pretty big difference. So everything is made of atoms. Atoms are made of smaller parts. And so your three subatomic particles are protons, electrons, and neutrons. So a proton is a positively charged particle, and they exist in the nucleus of the atom. So kind of like how the sun is at the center of the solar system and the planets orbit around it, you have the protons in the center of the atom, and then electrons, which are negatively charged particles, orbit around it. So it's a similar structure. But in this case, interestingly, like protons have weight to them, they have mass, and electrons don't. And we're not going to get into the meaning of how you can have a particle that doesn't contribute weight. We're just not going to worry about that. But the electrons are actually the most important thing for what's going on in how atoms stick together and how you get different kinds of molecules and how you get different kinds of minerals. But for example, like hydrogen is atomic number 1. It's way over here. So that 1 means it's got 1 proton and 1 electron, and it's just orbiting its happy little way, like the moon around us. But meanwhile, iron is over in here. It's number 26. So Fe stands for ferrum, which is the Latin word for iron. That's number 26. And so what that means is there's 26 protons in the nucleus of the atom, but then there's also 26 neutrons. And so neutron stands for neutral. It has no charge, but it does have mass. And so that's sort of where the weight of the atom comes from. So this 26 here is the number of electrons and the number of protons, but the atomic weight is this 55.847, because that extra weight comes from the neutrons. We're not going to really worry much about neutrons in this class, though. But you might notice the structure of the electrons here. So it's still a little bit like planets orbiting the sun, kind of. But there's definitely more than one of them in each orbit. So it's not like, Mercury and then Venus and then Earth and then Mars, and it's just 1, 1, 1, 1. You see a whole bunch of them. It's maybe a little bit more akin to like the asteroid belt, where you've got a bunch of stuff floating in sort of the same distance from the sun. But in atoms, that's called valence layers. And so each one is able to host a certain number of electrons. And so like you can only have 2 electrons in that first shell, in that first valence shell. But then in the second one, you can have 8. And in the third one, I think it's 16. I'm not going to count right now. But you can only have a certain number. And that makes a difference because, as it turns out, the outer shell likes to be filled, or at least balanced, but especially filled. And so because that outer shell isn't always filled, like here you've got a nice even number, but like let's say this were number 25, which is manganese, which is in some rocks. There'd only be 1 electron just hanging out in that outer shell, and that's not very stable. That is imbalanced. And so things might happen to make the atoms try to balance themselves. So are we in good shape with this structure so far? Is this sort of familiar from some other science class? I see nodding and yeah, thumbs up. All right. So it's really the electrons that are kind of the boss right now. So sometimes atoms are imbalanced and they do not want to be. So this is what I guess I should have advanced the slide sooner. So let's take sodium, which is a really common atom in rock-forming minerals. You're going to find a lot of sodium in things. So that's number 11, and it has got 1 electron in this outer shell. So again, in the first shell, you can have 2, in the second, you can have 8. The third is 18, not 16. Excuse me. But here, this third shell would love to have 18. It would want nothing more than to have 18 electrons in it, but it has 1. And so sodium is just very, very reactive. It wants to either get rid of that one, so it can go down to having only 8 in the outer shell and be full and happy, or it wants to consume 17 more, which is harder for it to do. So really what sodium is generally going to do is try to ditch that last electron. And so it's worth noting that doesn't make it not sodium anymore, because there's still going to be 11 protons and the correct number of neutrons in the nucleus of this atom. What's going to happen though is because it wants to ditch this electron, by getting rid of one electron, that means there's more positive charged particles than there are negative charged particles. So that means that the whole thing becomes a non-neutrally charged. So in a stable atom, it's going to have the same number of both, and it's going to have neither a positive nor negative electrical charge. But if it ditches an electron or gets one, that's changing the number of negative. And so if the number of electrons is less than the number of protons, it becomes a positively charged thing. And if it gets an extra electron, it becomes negatively charged. And so the word for a non-neutrally charged atom is called an ion, which is a word that is like used a lot, but I get the impression not a lot of people actually know what it means. And so an ion is just an atom that doesn't have the right number of electrons in it, basically. It has an electrical charge. And so there's 2 classes of ions. So you can have an anion, so that's pronounced anion, which has extra electrons. It's a little bit of a tongue twister. It has extra electrons and therefore is negatively charged. Or you can have a cation, which is missing some electrons and is therefore positively charged. And so you're going to run into both of those when you're really getting into like hardcore chemistry stuff. But in terms of forming minerals and forming rocks, we define minerals around which anions are in there, or which anionic groups are in there. And so we'll talk more about that next class. But basically, sort of a lot of the defining building blocks of minerals are these negatively charged groups that have extra electrons and want to like grab something else to get stuck to it. So does that make sense? So there are a couple of ways that an atom that is feeling imbalanced, like sodium, for example. Chlorine is another one that really is extra reactive. There are a couple of different ways that atoms can resolve this, but when they do, it's not just like the atom goes like, yeet, I'm done, and gets rid of that electron. It has to either take one from another atom or give it to another atom. But in that case, both of those atoms develop a non-neutral charge, and so they stick to each other because positive attracts negative, whether it's electrical or magnetic. So in that case, you have what is called an ionic bond. Basically, one atom steals an electron from another, and then they stick together thanks to the opposite charges. And so sodium and chlorine are really good examples because, again, sodium has this one electron in its outer shell, and it doesn't like that. And chlorine has all but one. Chlorine is missing one to be filled in that outer shell. And so when these 2 atoms get close to each other, the chlorine is just going to steal the electron from sodium, and then they're both happier. But then that sodium develops a positive charge because it's down 1 electron. The chlorine develops a negative charge because it's up 1 electron, and so they stick together. Just 2 magnets sticking together, or 2 electrical things sticking together. And that is called an ionic bond, and that is really, really common in creating minerals. Probably this is the most common one in minerals forming the way they do. So does this make sense? Just negative opposites attract is the principle here, and people will steal what they want in order to be happy, or give up things that are making them upset. If you want to anthropomorphize this a little. So any questions about ionic bonds? Cool. So then the next kind of thing that can happen is what's called a covalent bond. which basically means that there are some electrons. This is a lot sort of more of a mutual agreement between these atoms. It's not like I'm going to steal that and now we're stuck together. This is, you have some atoms that just kind of line up, so certain electrons will pass through the outer valence shell of multiple atoms. So, and so that's why they're covalent. This is a valence and they're sharing it. And so at any point, and carbon and oxygen are ones that do this. So rather than, so they have a more stable number in the outer shell, and it's easier for them to do this. So in this case, sometimes the carbon will have the correct number in the outer shell, and sometimes the oxygens will have the correct number. So the total number of electrons involved in this situation isn't a total number that would fill up the outer shells of all of them. So there's always fewer in somewhere. It's not taking care of the discrepancy, but because these things move around really fast and they're just trading so regularly, the atoms, each component atom is happy enough most of the time that this works. So does this make sense? Just kind of like if you take one of these, it would just kind of go, you know, it just could follow whatever path it wanted through here, maybe go over here. Just all of these shared ones on the edges are doing that. And this is also pretty common. I mean, again, carbon dioxide is really common. And so I think ionic still is more involved in minerals, but this is definitely a thing to keep in mind. So, and just again, keeping track of names, covalent, they're sharing a valence shell. Ionic, it's because they become ions and stick together. Good on that? So there's one more, and this one is a little less of an issue in this class, but not totally not an issue. So you can have what's called a metallic bond, and this only happens in metals. This doesn't happen in, and so the reason that this is less common in terms of rock-forming minerals is that most rock-forming minerals are not just metal. There are some that have more metal in them, but this is a lot more of the kind of thing that would be going on in like the core, which is all metal. But basically what happens is you've got some metallic elements that are not super happy with the number of electrons in their outer valence shell, and then there's just a bunch of electrons just floating around. And so some of this might be that like this element got rid of its last electrons, like I don't want that. And other ones are also getting rid of them, and so they're just kind of floating around in there. But because getting rid of that means everything is positively charged, those negatively charged ones kind of stick to everything. So this is kind of like a glue between positively charged ions. The positively charged ones are going to repel each other because they're not opposites. But these negatively charged, just loose electrons are going to still have enough charge to hold it back together. So maybe think of it kind of like, you know, how you have a bunch of bricks that are held together by mortar. Like they're held together by you know, it's kind of like that. So in this case, these electrons belong to no one, but they're holding everyone together. So does that make sense? Are there any questions about those? All right. So that is our basic chemistry lesson for now anyway. This is going to come back actually more in the next lecture, but keep it in mind today because it does kind of help explain how certain things form and what they get there, how they get there. So yeah, we've got these different ways that atoms can stick together, and they can stick together into minerals, which are building blocks of rocks. But now that we have that, I'm going to give you a more involved definition of a mineral. So here is your definition. A mineral is a naturally occurring, solid, crystalline material. It is formed by geologic processes, and it has a definable chemical composition. So in order for something to be a mineral, it has to meet all of these things. And so what does that mean? Naturally occurring means it occurs in nature. Something that's only made in a lab by humans isn't a mineral. Even if it literally satisfies like all of these other things, If it's only ever made by humans in a lab, it's not a mineral. It has to be able to occur in nature. Like, so you can have something where like you can have a man-made cubic zirconium or whatever, but that is still a thing that can occur in nature, so it counts. But there are substances that really are only made by people, and so they wouldn't be a mineral. So does that make sense about naturally occurring? So the next one then is that it has to be crystalline. So that means it has to form crystals. And we'll talk more about what that means in like 2 slides or maybe even the next slide. But it has to form these really distinctly shaped crystals. If it just forms an amorphous blob, it's not a mineral. So something like coal, well, actually coal is not a mineral for several reasons. So let's say glass. Glass is not a mineral because you can get naturally occurring glass, but because it's amorphous, it doesn't form specifically shaped things. It's not crystalline, so it's not a mineral. Makes sense? I think that'll make more sense in a couple slides too. Okay, next one, it has to be formed by geological processes, which basically means it has to happen in the earth. It has to be something that happens in the earth just by itself without the aid of living things. So like living things make plenty of stuff. Like, living things make bones, living things make poop, living things make all kinds of things that are not minerals that the earth does not form. The earth does not grow bones. The earth does not excrete. Well, I guess it excretes rock, but we're not gonna go further down that train of thought. But basically, there are a lot of things that are formed by nature that are not formed by geology. And so as we'll talk about in a bit with this, there are some kind of fine lines where there are some things that are minerals that are formed by geological processes, but living things can also form them. So there's there's a little bit of a fuzzy area on that one. But if it's only ever formed by life and not formed by the earth, it can't be a mineral. But things that are formed both by the earth and by life can be. Does that make sense? And then the last one is that it has to have a definable chemical composition. It has to have a chemical formula. So just like, think about water. Water is always H2O. It is always 2 hydrogens and its oxygen. That is the definition of water. If it has something else in it, it's not water anymore. If it's just O2, it's just oxygen. If it's CO2, it's carbon dioxide. Like those are by definition. And so any given mineral is going to have a chemical composition. So like quartz, which you've probably all heard of, is a very common mineral. And quartz is always SiO2. It's always a silicon and 2 oxygens. And that is its definition. So any mineral is going to have a chemical formula for it. And some of them, like quartz that I just said, can be really short. But some of them have like dozens of different things in them. And I can tell you now, I'm not going to make you memorize those. I'm going to ask you next time to sort of understand how different types of minerals are structured, but this isn't going to be a chemical formula memorization kind of class. I promise you that. So any questions about this definition? So a thing that I might ask you to do on either this test or on the final would be something like give you a thing and be like, is this a mineral based on these parts of the definition? So just kind of be familiar enough with the definition to do that. But cool. So crystals. Crystals are a key definition point for minerals. And here are pictures of a bunch of different crystals. Actually, let me go back one more. Well, no, I'll do it here. I'll do it here. But so does anyone know what a crystal is? Like, how would you define a crystal? Or at least describe a crystal?
How I usually think of crystal is like almost like glass, but not exactly. Like it's colorful glass. But even though there is colorful glass, those two are like separate. You know what I mean? It's hard to describe what a crystal is.
So, I mean, so definitely a lot of them are glassy, like this quartz up here, this halite down here. Ice crystals are kind of glassy, but you can have some like this bismuth, which is metallic, or this feldspar, which is opaque. But take a look at the shapes of some of these things. So are there any sort of things that stand out at you about the shapes of these?
Very angular.
Yeah, so angles is kind of a key thing. So you've got angles connecting faces. So yeah, some of these are more like dice looking kind of things. Got a cube over here, and halite is salt. It makes cubes. Salt is a mineral. You got a snowflake. Whoops. It makes these very, hexagonal crystals. And yes, ice is a mineral. Although if you were to say that on geology Twitter, some people might try to fight you. There's this thing that happens on geology Twitter that's called the Mineral Cup, where basically people vote on a bracket of their favorite minerals. And ice won last year, and a lot of people were really mad because ice is a mineral, but it doesn't form rocks and it doesn't behave like all the other minerals do in terms of geology. So anyway, that's like people got real mad about that. It was pretty funny. But anyway, yeah, it's angles. So angular is the word I was hoping someone would say. And so you have angles connecting different shaped faces. So like here you have right angles connecting squares and rectangles. Here you have, again, you have these rectangular faces and then a hexagonal face. Here are more, it's a little bit hard to tell from this photo, but quartz here is also hexagons, but rather than coming to a flat surface, it comes to a point. So basically, and then bismuth it does all of these weird things, but because it's a regular thing, it's a network of flat faces connected at different angles, it is still a crystal. And so, by that definition, we talk a little more about the structures of crystals. Yeah, and it's also worth noting that any mineral is always going to make the same thing. Like you're not going to get quartz that does one thing and quartz that does a completely different thing. The crystals of one mineral are always the same shape. But yeah, when we're talking about a crystal, we talk about faces. So like I was saying, like this surface of this quartz is a face. This surface is also a face. This is an angle between faces. And so sometimes the angles vary, but the number of faces are always going to be the same. Or sometimes the angles might switch it up a little, but it's still, or the length of the faces might be different. But like a quartz is always going to be 6 rectangular faces at 120-degree angles that come to a point. And again, different things make different sizes, shapes. Different things have different numbers of faces, different angles, whatever. The important thing is just that structure of faces and angles is what defines a crystal. But how does that form? So that forms because of the configuration of atoms. That forms because the atoms in that element, in that mineral, have stuck together in a certain way based on the kind of bonds that we just talked about. And based on the way they stick together, sort of which atoms there are, how many of them there are, who's sharing which electrons, they're going to stick together in a very certain configuration. And that configuration kind of forms a lattice work that ultimately shapes the crystal. So like this example, so this is the Washington Monument being fixed after earthquake damage. There was an earthquake in 2011 that caused damage to the Washington Monument. And they built this scaffold around it to fix it. But it turned out to be a great illustration of what a crystal lattice looks like. Because here you have this obelisk. You have 4 faces at right angles coming together at a point. And there are some minerals that are absolutely this shape. But you can see kind of this network of lines crisscrossing the surface. So if you were to sort of zoom in on a mineral, on a crystal face with a really powerful microscope, and there absolutely are microscopes that can zoom into the atomic level. I think we might even, no, maybe we might have one at CSUN. I don't know. I don't use it. I'm an earthquake physicist. But you can actually see this very regular network of how the atoms are lined up to make a mineral. And so again, different minerals, because they have different chemical formulas, are going to have different numbers of atoms arranged in different ways, which turns into different shapes. So does that make sense? Does anyone have any questions about any of that so far? Cool. So, but when you're identifying a mineral, actually both the crystal structure and the chemical composition matter. So I know I just said that, you know, every mineral has its own set of atoms in it, has its own chemical formula, and as a result, the atoms are going to fit together in a certain way that makes a certain shape. Now, remember I said, though, that there's more than one kind of bond. And so sometimes you can have something with the exact same chemical formula get stuck together with one kind of bond and make one shape, while in another kind of condition, that same chemical formula could get stuck together with a different kind of bond, and that makes a different shape, which makes a different mineral. So a really common example of this is the difference between like common pencil graphite and diamond. So they both have the exact same chemical formula. They are both just graphite. They are both just carbon, excuse me. It's literally just carbon. But in graphite, the conditions are such that the bonds are weak and they form these hexagonal sheets. And those sheets are held together by strong bonds, but then there's weaker bonds between the sheets. And so in that case, that's why you can write with graphite, because the bonds between those sheets are so weak that just rubbing them across paper breaks them and you leave graphite on the paper. That's how a pencil works, by breaking chemical bonds. And so that's going to form in some conditions, but in totally different conditions, those carbon atoms are going to arrange themselves in a much sturdier network of strong bonds throughout. And in that case, you're going to get diamond. And so, and in diamond, the shape of those bonds leads to this sort of pyramidal, or sometimes bipyramidal. So, you know, pyramid on one side, pyramid on the other side. It's going to lead to a structure like that. So you can't just necessarily look only at a chemical formula and go, yes, that's this mineral. Because I could just show you carbon. I should just give you a letter C, and you wouldn't be able to tell me just seeing that, whether it was diamond or whether it was graphite. But you're hoping it's a diamond, but you wouldn't be able to tell me. But also, there's only a certain number of geometries that can exist, and certain kinds of bonds and certain groups of atoms will form similar shapes. So like I could show you something that's a hexagon, a hexagonal prism with a pyramid at the end, and you could go, yeah, that's quartz, but it might not be. There are other minerals that are actually much rarer than quartz that form the same shape. Or like there's a lot of things that just form cubes. So when you're trying to figure out what's what, both the chemical structure, both the crystal structure and the chemical composition are important for telling minerals apart. And in terms of building rocks as well, in terms of how these things stick together into rocks, again, both of these things matter a whole lot in terms of what you get. And that doesn't just affect what kind of rocks you get, but also how they move, how they change, how they erupt or not. Again, we're going to be talking a lot about the balance between chemical composition and crystal structure. So for igneous rocks, for volcanic rocks, which is going to be our first topic after the test, both of these things matter a whole lot. For sedimentary rocks, it actually, neither of them matters that much at all. For metamorphic rocks, it has a lot more to do with this changing structure than it has to do with what the chemical composition is. But this is going to come back again and again and again. So any questions about this? All right. So we've got minerals. We've got atoms. So how do minerals form? I mean, they can form by, you know, atoms sticking themselves together into molecules which stick themselves together into minerals. We talked about how atoms stick together, but in the real world, in terms of geology, like you can have atoms stick together for a lot of reasons that are not geological. But what we're going to do for today, for the rest of today, is talk about how minerals form and then also how they get destroyed. Because, you know, where does this stuff come from? How do we get these building blocks that eventually turn into rocks? And there's a couple of major ways that that happens. The first one is just solidification from a liquid. So this is a picture, I think this is from 2 years ago, or maybe last year is when I last taught this class. So this is Chicago. This is a very bad winter when it was colder than Antarctica. But what do you see in the lake? So that's Lake Michigan. What is going on in there?
It's freezing over.
Yeah, it's freezing over. And so liquid water, which is not a mineral, is solidifying into ice, which is a mineral. And so basically this process is, it is slowing down the atoms enough that they solidify and stick together. So just like you can get ice out of water freezing, you can get solid minerals out of liquid stuff. Often we use the term geothermal fluid for liquid earth stuff because geo, earth, thermal, warm, fluid, liquid. So if you get to a thing where the temperature of a geothermal fluid gets cold enough that some of the minerals start to solidify out of that liquid. Although when I say cold enough, we're still talking like thousands of degrees. It's still really stinking hot when that happens. But it's the same exact idea as water freezing into ice. It's just liquid minerals or liquid atoms getting cold enough that they consolidate into solid minerals and form crystals. So does that make sense? Just happens that because that's at such a high temperature that happens at, it's almost never on the surface of the earth, and it's just something that we never really think about it because all of the rocks you're going to touch, all the minerals you're going to touch on the surface of the earth are solid already. But this is actually a really big thing going on, especially as you get kind of in that boundary zone lower down in the crust where it's still really hot, but not so hot, but not enough pressure to keep it solid. And also this is a big deal for volcanoes, but we'll get there in a couple weeks. Any questions on that? So then another thing you can get is you can do precipitation from a solution. So precipitate is to fall out. So like when we talk about precipitation in the weather, it's rain usually falling from the sky. It is falling out from a cloud. So in that case, liquid is precipitating out of a gas, like a cloud is gas and rain is a liquid. But you can also precipitate a solid out of a liquid. So in this case, this example is rock candy, which is not, and that's not a mineral because sugar is not a mineral. Sugar does not form from geological processes, it forms from biological processes only. But it's still a good example of this behavior. So have any of you made this stuff? I mean, if you want to eat some pure sugar, this is the way to eat some pure sugar. But basically what you do is you make a sugar water solution and then like put either a stick or a string into it. And over time, sugar crystals will start to build on the stick or string until you get something that looks like this. And it wouldn't be a rock because it's just one substance, and it also can't be a rock because sugar is not a mineral. But it's the same idea of usually if you put something in there, like if there's some sort of seed or like framework that minerals can start growing onto, they will. And once one crystal starts growing, more and more atoms will stick to it, and the crystals will get bigger and bigger. So this is another thing that happens often in a geothermal fluid situation. Oh, I see we have those, but we add saffron to it and add it to our tea. Oh, that sounds really good. Yeah, I guess you can make like fancier versions of these. That makes me want to try that. That sounds really good. But yeah, this is This also happens in geothermal situations, but the difference is rather than the fluid necessarily cooling, it's that the minerals will start latching on to something else and growing on it. So you need something in there for this to start happening. And so it could be like another rock that you drop in. It could be just the edges where it's colder and it starts growing on the wall of something, kind of like in a geode. If you've ever, do I have a geode in my room right now? No. Thought I did. I think it's in my office. Kind of like, you know how in a geode where it looks like just a gray rock and you open it and there's a bunch of crystals inside? That was basically those crystals precipitating out of a liquid onto the walls of that rock. Does that make sense? Cool. So you can also have a situation where you can precipitate crystals out of a gas. But that's pretty rare. So in this case, it's the same idea. It's just instead of a solid condensing out of a liquid, it's a solid condensing out of a gas, which again, you're switching between two different phases of matter. So it's not that common. But this tends to happen in volcanic settings. So this is a picture from, I believe this is from Hawaii, and this is a volcanic vent. And so what's coming out of this is sulfur-rich volcanic gas, really nasty egg fart smelling stuff that will choke you. But sulfur gas, when it's exposed to cold rock at the surface of the earth, cools down so quickly that it doesn't pass through a liquid phase first. It just turns straight into these sulfur crystals, which look like these sort of pointy ferns. And so all of this yellow stuff here, if you zoom in on it, would look like these crystals. So again, this requires a really, really big temperature contrast. It requires having something that's hot enough to be a gas and cold enough to be to create a solid. But this does happen. But otherwise, it's the same idea as the liquid to solid one. So are we good on that? Again, this gas will strangle you. This is bad news. But yeah. So one of the next things that can happen, I mentioned there's this weird gray area with stuff being created by living things. And I did say stuff that is only created by living things cannot be a mineral. But a lot of mollusks, a lot of clams and scallops and snails and things that make shells are doing what's called biomineralization. And so what they are doing is they're kind of making a biological framework and then actually pulling in mineral content from their environment and using it to build their shells. So they're not like producing, and so all of these are calcium and carbon based minerals. And they're not like producing all of that with their bodies. Like, I mean, they're not just like metabolizing it. But they're kind of, their body processes sort of draw in those things from the environment. I guess it does maybe pass through them. I'm not super familiar with like slug biology or anything, but basically they're taking these molecules out of the environment and using them to build up a shell. And so if you were to look at these shells really close, like under a microscope, again, a very detailed microscope, you would see that actually there are these microcrystal structures within the shell. And so this is a case where, because those same minerals can form without the help of a clam, they still count. Like you can find these same crystal structures and chemical formulas elsewhere. This is just sort of the exception to the rule. This is where something that is formed by biology still counts because it can also be formed by geology. So I know that's a little bit of a tricky one, but does that make sense? Cool. So there's a couple more. So this one's a little bit more complicated. So you can get something that is called solid state diffusion. And so like rather than pouring a liquid through a solid, or actually you could do it pouring a liquid through a solid, it basically says over time stuff is gonna like phase through each other and just kind of fuse together. So like imagine you were pouring a liquid through a strainer, but instead of the liquid, or like maybe you're pouring a liquid through a strainer you didn't clean very well, let's say, and as it goes through the strainer, the liquid is going to pick up particles of whatever, it's going to pick up your used pasta sauce or whatever, and you're going to end up with kind of a different substance on the other side. So this is basically, except in this case it's not liquid. So in this case it's one of those weird things that kind of happens at high temperature but also high pressure, where again the high pressure means that the rock can, the high temperature and high pressure means the rock can flow while still being solid. And so in this case, these things are just trying to flow through each other, but then end up kind of just melding together in a whole new substance. So this might be a case where, like, let's say you had some metal and something that wasn't metal, and they tried to sort of diffuse through each other and eventually formed a mineral like, say, olivine, which has a lot of silicon but also has a lot of metal. So does that make sense? Just that idea of like things sort of trying to squish past each other and then just getting stuck together. Like this is one of, I think this is one of the less intuitive ones. So don't worry about this one too much yet. But this is going to come back, especially when we talk about metamorphic rocks, because this is actually a really big process that controls how rocks can change from one type to another. But we're going to get back to that honestly in a couple of months. So don't stress too much if you don't get this one yet. Yeah. So those are basic ways that you can make a mineral. You can basically freeze it, or you can condense it from a liquid, condense it from a gas, have some sort of critter make it by pulling it out of the environment, or you can do this. Any questions on any of those? So if you don't, then with that in mind, wow, excuse me. I'm going to ask you to use some deductive reasoning based on what we just talked about, and ask you, what do you think are some ways that minerals can get destroyed or recycled?
Pressure.
Yeah, so pressure can definitely be involved. So just like in this case where pressure actually caused these things meld together, you can actually have pressure separate things as well. But I don't want to advance the slides yet because I want to see how many of the others you guess before I advance the slides, but I will get back to that.
I want to say heat. Like maybe you can heat up a mineral and it can get recycled into another.
Yeah, so what happens when you heat ice?
Oh, it
It melts.
turns into water.
Yeah, so that's a big one. Yeah, melting is actually one way you can get rid of any mineral. You can get rid of ice by melting it, unfortunately for our friend the polar bear. But you can also melt all kinds of things. You can melt everything if you get it hot enough. And again, on the surface of the Earth, it's usually not hot enough to do that. But in volcanoes or in sort of the lower, especially in volcanoes, but in certain places where there's sort of in the lower crust or in the mantle, usually again at that transition zone at the bottom of the crust where it's warm enough to melt but not enough pressure to stay solid, you get a lot of this going on. So yeah, you can turn something from a crystal back into like liquid bits. And so again, even if it's all like SiO2, it can't be officially mineral quartz unless it's a solid crystal. As soon as you melt it, it's not a crystal anymore. That would make sense. So following this same line of reasoning then, if you can freeze and you can melt, what are some other ways do you think we could get rid of minerals based on how we form them?
turning it into a gas.
Yeah, so you can turn something into a gas or a liquid, right? So here we turn it into a liquid. You can turn something into a gas. But let me ask you, what would be the opposite of making that rock candy? Like what would happen if you dunked that back in water?
It would dissolve.
So you can dissolve minerals. So this is an antacid tablet, but that's actually mostly a calcium carbonate mineral. Yeah, so basically in this case, when you melt something, the difference is it's turning from something that is one chemical formula into something that's the same chemical formula, just liquid. But when you are dissolving something, or when you're precipitating something out of solution, it's kind of separating out some stuff. So the fluid had a mix of stuff, and it turns into a fluid that's one thing and a solid that's another thing. And so dissolution is the opposite of that. So this started as your Pepto-Bismol tablet, or Alka-Seltzer, I think is what this is, and your water. It started as two very different things. But as soon as you drop that into the water, it has this reaction where it dissolves and turns into a mix of water in this stuff. So it turns into a sort of mishmash of things rather than two chemically discrete things. So does that make sense? The difference between melting and dissolving? Or between freezing and precipitating? Freezing and melting, you're just dealing with one chemical in different states. And precipitating and dissolving, you're dealing with a mix of two different things, either separating out or coming back together. And you can absolutely do this from a solid to a gas as well. But also that's pretty uncommon, again, because of the temperatures needed to do that. So that's another like pretty much only in volcanoes kind of thing. But that's also partly why volcanoes are so cool, because they have such extreme things happening in them. The volcanoes part of this class is one of my favorite parts to teach, and that's coming up in a few weeks. But yeah, I don't think I don't have a slide for dissolving into gas, but it's the same idea. But what else? What do you think the opposite of biomineralization might be? You know, is there an opposite to a creature taking in stuff and making a mineral? So let me ask this: what happens? What happens when you take your vitamins and minerals?
Your body absorbs them.
Yeah, your body absorbs them and digests them, and or it metabolizes them. And so that's another thing that can happen. Yeah, and it transfers it to energy. Yeah, very much so. So metabolism is kind of the opposite of biomineralization. It's basically, and we are metabolizing minerals we eat. In terms of geology, it's usually microbes that are the ones that are doing this, because microbes will actually just eat rocks, kind of. I guess we're doing that on a smaller scale, but most of ours are kind of tangled up in like salad or whatever. I was about to say in things like burgers, but I don't think there's a lot of minerals or redeeming nutrients in there. But yeah, metabolism is something where you go and eat or consume a mineral, and your body breaks it down into something, either into component atoms, into totally different substances, or into a biological byproduct, for example, that is definitely not a mineral anymore. So does that make sense? Like if you were gonna, again, if you were gonna eat that antacid tablet, it starts as basically being a powdered mineral, but it's not going to be that anymore by the time it hits your stomach acid and passes through your digestive system and out the other end. I did not expect to talk about poop that much in this class, but it is actually part of, it is an actual process that is involved in that. That again is a non-geological thing. So even if it might have atoms in it that are part of minerals, it doesn't make minerals. So yeah, for every creature that can take in something and make it, there's other creatures that can take it in and break it down. And I apologize for this extremely old meme, but I still think it's funny. Anyway, does anyone remember this meme? Or is it time to change the slide? Am I just making myself look old? I think I'm just making myself look old. Anyway, oh, you're nodding. I mean, I admit it, I'm old. I'll keep it, okay. All right. I see a question mark. But I mean, basically just the whole meme with this was the phrase, they crave this mineral, and it just took off. They're in search, know your meme. But yeah. Also,
they're licking the rock?
They're licking the rock, like many geologists do. So in this case, they're licking salt deposits off the rock, and salt, halite, is a mineral. And the reason actually geologists will lick rocks is partly to see if there's halite in there. But also, as we'll talk about more later, sometimes there's textural differences that you can't tell with your fingers, but can tell with your mouth. So all of the jokes you heard about geologists licking rocks are true. But we're not gonna, even if we were an in-person class, we wouldn't be doing that. That's for geology majors.
What does it taste like?
Well, halite is salt. It's literally salt. So if you were to lick that rock, it would taste like dirty salt. But yeah. But any questions about metabolism? So this last one that I'm going to show you is, it's not quite the opposite of not quite the opposite of the diffusion. So I guess I don't think, I don't have another slide for the opposite of diffusion. But as I'm sorry, I already forget who mentioned the pressure separating things, but that was absolutely a thing that happens. It can kind of pressurize and separate out, like we talked about with the Earth forming the way it did. But one last way, I guess I can add a slide for the next time I teach this. But one last way that you can break down minerals is through chemical reactions. So like rust, for example, isn't a substance. Rust is a chemical reaction. Wherein I guess the iron, with a car like this, it's probably just straight up iron. The iron in this very old car is broken down into rust, which comes from a chemical reaction between oxygen and iron. And so I guess iron doesn't really make crystals, it's not really a mineral, but you can have the same kind of thing happen to minerals. And actually, if you have a mineral that has a lot of iron atoms in it, it can oxidize. Oxidize is a more general term for things like rust. So in this case, just the oxygen interacting with these metallic atoms breaks them down into rust. And so actually, that's why in some cases you'll see, if you go to some volcanic places, you'll see black rocks and then you'll see red rocks. A lot of times the red rock comes from basically the iron in that rock rusting. But yeah, this breaks the structure of the mineral down, and usually not only breaks down the chemical formula, turning it into something else, but also by introducing the oxygen, by introducing the chemical reagent. It also it's changing the chemical formula and also breaking down the crystal structure. So usually this both destroys the mineral has a set chemical formula and the mineral has a set crystal. This does happen in nature. This is a geological process, but it can still destroy things. So any questions on that?
I know iron isn't necessarily a crystal, but is there like a way? I know that there's chemicals there are chemicals oh my god, I can't speak. Like there's products you can buy to get rid of rust. Is there like any oh, wow, I'm having a bad day today. Is there any way to do that to crystals? Like they interact with like oxidization.
So I think again, I don't know the details of rust cleaner, but I don't think rust cleaner is undoing a chemical reaction so much as just literally scraping that stuff off and actually probably putting some sort of resistive barrier on the metal so it doesn't rust again. Like I don't know of any substance that cleans up by like undoing the chemical reaction. But certainly like there are other things where like there are certainly situations where you can add a chemical to another chemical and it turns into a mineral, like it turns into a formula that can consolidate into a mineral. Like that absolutely happens. It kind of ties into the diffusion thing as well. So that can happen. Again, it happens a lot in like volcanic settings because it gets hot. Volcanic settings are where you get the most heat and fluid and liquid stuff. So most of the time when you're dealing with a process that involves liquid, it's usually related to a volcano. Although sometimes a lot of it is, you can get some in like the ocean, but it forms pretty different stuff. Or in water in general. But we'll talk a lot more about how that stuff forms when we talk about sedimentary rocks in October. Yeah. I think that's, yes. But yeah, are there any other questions about any of these? Or anything today? Okay, so that's actually where I'm going to cut it off for today. So we've still got 14 minutes, so hopefully that makes up for me talking about plate tectonics a little too long. I will still try to put up like a short video about the triple junction stuff because we were rushed at that at the end of last class. So I'll try to get that up, but it might not be until a little later in the week because I'm actually at a virtual conference this week and I'm taking some time to teach this class anyway. But yeah, so that'll be up. But starting next time we're going to talk about ways to tell different minerals apart and then get into the structure of silicate minerals in particular. Because silicate minerals, you might have noticed some terms about that in your vocab thing, are the main rock-forming minerals in the Earth, and especially in the crust. And so they're going to be kind of the most relevant group of minerals to the rest of the class, silicates and then carbonates to a lesser degree. But we'll get more into that next time. So again, your quick quiz is going to go up right after class. There's not another new vocabulary because we're still talking about minerals next time. These slides will go up after next class because it's still about minerals. And I think that's it. So if you want to stick around and ask questions, or if you want to stick around and talk about fires, I can do that. But if not, you may go, and I will see you all on Wednesday.
Thank you, Professor.
Thank you.
And take care of yourselves. Try not to breathe that too much out there.
All right. Thank you, Professor.
Thanks. Are those of you who are still in here waiting to ask something, or are you just hanging out? Gonna take that as a just hanging out. So if you do have a question later, you can either come to my office hours tomorrow or just email me. But have a good one.